Hello there. In this video, we are going to talk about modeling with functions. So this is not the catwalk kind of modeling. This is even more glamorous. It's representing a physical situation using a function as a model for that situation. All right, so let's go take a look at an example, and we'll see what we can do with it. So here's our example. See if I can get rid of some of the glare here. Okay, that looks a little better. Suppose that your distance in miles is given by this function. D for distance. D of t is equal to 30t plus 100, where t is time measured in hours. Now, when we previously looked at functions, we called them f of x. Well, f is just a letter we happen to choose for the name of our function because f stands for function. But you could use any letter, right? So because we're measuring distance, instead of f, we decided to call our function d. Instead of x is just a letter that we use to denote the variable that we're plugging into the function, right? Well, you can call it any letter. In this case, since we're measuring time, we're going to call it t, right? So get used to that. Functions can have different names and different variables. Okay, so what does the y-intercept for this function represent? Well, remember how we get the y-intercept. The y-intercept, if I were to graph this function, right, it would have some. First of all, it's a linear function, right? It's in the form mt plus b, right? D of t is in the form mt plus b, so it's a linear function. So I can draw its graph as a straight line. What is the y-intercept? That's this point right here. That's the point 0, comma, and remember, any point on the line is of the form d of, so it's x comma, any point is of the form t comma d of t. So when t is 0, this is d comma d of t comma d of 0, right? And so the y-intercept is d of 0. So the y-intercept, the y-coordinate of the y-intercept is a point. If I want the y-coordinate, it's d of 0. And d of 0, I can compute that by just plugging it in here, right? It is 30 times 0 plus 100, which is just 100. So I found out what it is, but what does it represent? Well, let's read the function again. Your distance is given by d of t, where t is time. So this is the distance when time is 0, right? D of 0 is the distance at time 0. So this is our initial distance. So our distance, when we start our journey, we are already 100 miles from some reference point. And I think I gave away what are its units. Its units, this is a distance, and distance is measured in miles, so the units are miles. So the y-intercept represents our initial distance, our starting distance, and our units are miles. Okay? Okay. Did it matter that this was a linear function for any of this? No, it actually didn't matter. We never used the fact that it was linear. This would apply to any function. Okay. Moving on to part B. What does the slope represent? What does the slope represent? Well, the slope, that's the m here, okay, which is 30, right? The slope is 30. What is that telling us? Well, let's think about how we would compute slope. So let's go back to our graph. Let's draw it again. Here's t, that's time, and here's the y-axis. Here's our line, our graph of our function. How do I measure slope? Well, I take 2 points on my line, and I measure the rise divided by the run, right? Now, the rise is the change in y values. That's the change in values of d, right? So remember, the slope is y2 minus y1 divided by x2 minus x1, except here we have t2 minus t1. Well, how do I get the y values? Well, remember that when I graph a function, we're graphing y equals the function value. The height, in other words, the y value of every point is the value of the function. So these y's are actually the d's. y2 is d of t2, and y1 is d of t1. See, it came from 2 points. t1, d of t1, that's maybe this point. And d2, t2, d of t2, that's this point. And when I take the slope, it's the difference of the d's divided by the difference of the t's. Well, what are the d's measured in? The d's are measured in, well, let's compute the slope of this thing. Well, we actually don't. We don't need to. We know what it is, right? We know that the line is in the form mt plus b, so we know the slope is going to be 30. So no matter what values of t we choose and we compute this, we're going to get 30. All right? So we know we're going to get 30 as the answer. And you could try it. Pick different values for t. Any numbers you want. Any numbers you want. Plug them in here. Plug them in here. You get 30 every single time. Guaranteed. But what are the units? Well, if I look at this, I'm taking the difference of distances in the numerator. So these are going to be miles. And I have the difference of times in the denominator. Well, these are measured in hours. Miles divided by hours, which we would usually read miles per hour. Well, I just found the units, right? The units are miles per hour. What do we measure in miles per hour? That's the speed. That's the speed at which we're traveling. And another name for speed is rate. That's the rate at which we are moving, or the rate at which the distance is changing. So the slope represents the speed, but in general, the slope represents the rate at which the function is changing. In this case, our function is d. If the slope is positive, as it is in this case, we know we are moving forward. If the slope is negative, that means our distance is decreasing, so we're moving backwards. So the slope can be positive or negative depending on which direction we're going. Okay. Part C, find the distance from home after 2 hours. Okay. Find the distance from home. So they want us to find the value of d. All right, so they want to know what d is after 2 hours. 2 hours, that's time, right? So they're saying the time is 2. They're telling us that t is 2. Now, it's a little bit of weird the way we use the English language. When we say after 2 hours, find the distance after 2 hours, what we mean is the distance at exactly 2 hours. It's a weird way in which we say it, but that's what we mean. Somebody says, how far were you after 2 hours? I mean, where were you when you were exactly 2 hours? So t is exactly 2. So t is exactly 2 hours. And I want to know what the distance is. Well, the function tells me how to do that. The distance at any time, let's leave off the units. Let me write these in here. D of 2 is, well, let's go to my function's formula here, 30t plus 100. All right, so it's 30 times 2 plus 100. Let's simplify this. 30 times 2 is 60. 60 plus 100 is 160. And distance is measured in miles. Right? So my answer would be 160 miles. Now I want to show you something, and that's what I was starting to do here. I want to show you how you can actually carry the units along, and it's actually really good to do that because it gives you a check at the end. If the units work out, then it's an assurance that you didn't make a mistake. It doesn't guarantee it, but if it comes out wrong, you know you made a mistake somewhere. So let me do this again, but with the units. 2 hours. Now, d is equal to 30. What are the units on the 30? We said the speed was miles per hour. Times t, 2 hours, plus 100. Well, 100 was our starting distance, and that was measured in miles, right? So that's miles. Now look what happens here. Hours divided by hours, they cancel. So I have 30 miles times 2. That's 60 miles. Just treat the unit like a variable, right? Just treat it like x. And what that means is I can only combine things if they're like terms, if they have the same units. If these units ended up being different, aha, then I know I made a mistake. And that's why this is a great way to check your work. Carrying the units is a great way to see if you've made a mistake. Because if at the end the units don't work out, well, you know you goofed somewhere. Also, it's a great way to figure out how to solve a problem, because sometimes you can get an idea how to solve a problem simply by seeing how you can get those units to work out. That's a little bit sketchy, because just because you get the units to work out doesn't mean you did it right, but it gives you an idea for something that you might check to see if it is the right way to do it, right? But yeah, we got miles. We should have gotten miles. We're measuring the distance, right? So great. Let's go to the last part here. Suppose you live on the equator, all right, and you travel along the equator away from home. How long until you travel all the way around the Earth and arrive back at home? All right. So you flat earthers out there, you're going to have to bear with us and assume that the Earth is round for this one, all right? So we live on the equator, we travel all the way around the Earth and arrive back at home. So, wow. Let's see. What are we explaining here? Well, what are we asking? How long? So we're looking to find, we want to find t. We want to find t. So t is an unknown. Travel around the Earth. Well, do I know the distance? Well, maybe not offhand, but I could figure it out. Okay, well, you can look that up, all right? And it comes out to 24,901 miles at the equator. Okay, so I want my distance. So here's a picture of what we're doing. We're starting at home over here, right? I'm already 100 miles from home, right? But I want my total distance from home to end up being all the way around the circumference. So that means I want d of t to equal that number, 24,901. But I have an expression for d of t. 30t plus 100. Okay, so let's do that. So that's 30t plus 100 equals 24,901. There's an equation we can solve for t. Okay, pause the video, solve the equation, and I'll meet you back here. Okay, so 3, 2, 1. All right, so what do? Subtract 100 from both sides. Oops, how did that happen? Okay, divide both sides by 30. And let's see, I get t equals 24,801 over 30, which simplifies to, thought I put this in my notes. Yeah, there it is. Approximately 826.7. 826.7 what? Well, time is measured in hours. And actually, if you check the units, 30 is in miles per hour. These are in miles. This is in miles, right? So when I subtracted 100 miles from both sides, I was left with miles, right? I divided both sides by miles per hour. Miles divided by miles per hour, well, the miles cancel, the hours come up to the numerator, right? This is miles divided by miles per hour, and I'm left with the miles divided by miles per hour will give you hours. So just a quick check of units, it works out. Okay, so that was dealing with a linear function. Let's just go through some of the things we learned here, okay? The y-intercept is given by d of 0. That's the y-coordinate of the y-intercept. The y-intercept is 0, comma d of 0. The slope represents the rate of change, and the units are the y units divided by the x units, or in this case, the t units. Maybe that's a good thing to point out. Y units divided by the x units. In this case, x was t. And if you want to find the value of the function, you just plug in the value of t. If you want to find a value of t, you set up an equation to solve. You write it down, and then you solve. Okay? So that's it for this video on linear functions. Okay, so I'll see you in the next one.